Welcome back for Lecture 5. Today we'll be talking about Hamiltonian paths and cycles and directed graphs. So let's get started with this problem. Suppose you're biking through a city that only has one-way streets, and you want to know if you can plan a route that visits all of the ice cream parlors in the city. We're given the following one-way streets. So there's a street that heads from parlor B to parlor A, a street that heads from parlor D to parlor A, street that heads from parlor D to parlor B, and etc. Okay, these are all one-way streets. So how can we model this scenario with a graph? Oops. Okay, so in other words, what are our objects, our vertices, and our connections, which are our edges? Well, I would say the objects are the ice cream parlors, and the connections are if there's a street going from one parlor to the other. So we can draw all of these. See, we have parlor A, B, C, D, E, and F. Okay, and let's draw in our edges, our connections. So there's a street from parlor B to parlor A. But notice when I draw in this edge here, we're actually losing some information, okay? Because this is a one-way street. We can only go from parlor B to parlor A. We can't go from A to B. Okay, so how can we note on this graph that this is a one-way street? Well, we could just draw in an arrow, right? And we can do that for all of our one-way streets. Okay, so we have a street from D to A, and we'll draw an arrow pointing towards A. On this edge, we have one from D to B, draw an arrow pointing towards B, from E to D, from E to F, from B to C, from C to F, okay, and from C to E. I'll draw it going around this way. Okay, so this is what's called a directed graph. It's a graph where the edges have directions, okay? And we assign these directions, or we notate these directions by using arrows. So recall that an Eulerian walk is a walk, which was a sequence of distinct edges we can trace in the graph without picking up our pencils. That uses all of the edges of G. So in a directed graph, we must move across an edge in the direction the arrow is pointing. Why does this make sense? Well, we wouldn't want to do a walk going from A to B because there's no street that goes from A to B. If we're going to use up this edge, we want to go in the direction of B to A. So a directed walk is a walk that follows the arrows of G. A directed path is a path that follows the arrows of G, etc. So if we had a word that we had before in a graph that wasn't directed and we're calling it directed, it just means it has the same definition, but we're following along the arrows or the directions of our directed graph G. So let's look at this example. Does this graph contain a directed Eulerian walk? If so, find one, and if not, explain why. So pause the video and try to figure that out. Okay, so does this graph have a directed Eulerian walk? Okay, so we want to follow along the arrows of this graph, and we want an Eulerian walk. So a set of distinct edges we can draw without picking up our pencils, and we don't want to visit any edge more than once, but we also want to visit all of the edges of the graph. So this one does not contain a directed Eulerian walk, and there are a few problems in here, but we can look at this vertex, for example. Okay, let's say we're at this vertex. We'd have to start here, right? Because we can't enter the vertex by any edge. And let's say we follow this edge first. Okay, once we leave here, we can't get back to this vertex again, so there's no way to follow this edge anymore. Okay, so no, there's no directed Eulerian walk. When we say a directed graph G is strongly connected, if for any pair of vertices V and W, there's a directed path from V to W. Okay, so let's look at these two graphs and determine if they're strongly connected. So pause the video, think about that for a minute, and then come back. Okay, now that you're back, are these graphs strongly connected? So is there a path between any two vertices? Well, here, yes. Notice we can go all the way around following along these arrows. So if we start at any point here, we can get to any of the other vertices by just following the flow of this cycle. But then in this graph, okay, let's see. So what's wrong with this vertex right here? So I just covered up this arrow. There's no way to get to it. The only edges are leaving this vertex. So if we start at this vertex, for example, there's no directed path from this vertex to this one. So this first graph is strongly connected, and the second one is not. Okay, so the in degree of a vertex V, which is denoted by INDEG of V, that's the number of edges heading into the vertex, and the out degree is the number of edges heading out of that vertex. Okay, so in this example, if we look at this vertex V right here, what's the in degree? It's the number of edges heading into the vertex or directed towards that vertex. So there are 1, 2, 3 edges going in towards V, so the in degree is 3. And there's 1 edge heading out, so the out degree, oops, it's not 4, is 1. So we say a directed graph is balanced if the in degree is equal to the out degree for all of the vertices of that graph. And that gives us this theorem. A directed graph G has a closed Eulerian walk if and only if it is balanced and strongly connected. Okay, so balanced meaning the in degree is equal to the out degree, and strongly connected meaning there's a directed walk between any two vertices. So let's think about why this is true. We'll just think about one direction of the proof. So what that means is we'll assume this side of the theorem that a directed graph G has a closed Eulerian walk. So why does that imply that that graph is balanced? Why is the in degree equal to the out degree for all of the vertices of G? So try to think about that for a minute. Okay, so let's think about what happens in a closed Eulerian walk. Right, we're going to use up all of the edges, and we're going to end where we started. Okay, so if we use up all of the edges, that also means we have to visit all of the vertices, right? So each time we enter a vertex, we also leave it. Okay, so we're following an edge that goes towards V, and then we're following an edge that goes away from V. Okay, and that happens each time we visit the vertex. So every time we visit each vertex, we must also leave it. And we visit the vertex along an edge that is directed towards V, which contributes to the in degree. Okay, and we leave a vertex along an edge that is directed away from V, contributing to the out degree. Okay, and then still assuming the same thing, that G has a closed Eulerian walk, why does that mean that G has to be strongly connected? So why does that mean there has to be a path from each vertex V to any other vertex W? So think about that for a minute, pause the video. Okay, so again, by the same thinking in this last question, we have to visit each vertex in an Eulerian walk. Okay, and it's closed, so it loops around. Okay, so if we pick any vertex V, we visit it in the Eulerian walk, and if we follow along that closed Eulerian walk, we can get to any other vertex because they're all included in the walk. Okay, so if we start at a vertex V, okay, which must be included in the Eulerian walk since all edges are included, we can eventually, or we can follow the closed Eulerian walk until we get to any other vertex W. All right. So let's look at this example. Let's determine if this graph has a closed Eulerian walk and try to do it without just looking for a walk at first. And if there is one, find it. So pause the video and think about that. Okay, so let's think about, since we're not looking for an Eulerian walk specifically at first, all we can do is use this theorem we have. So it said a directed graph has a closed Eulerian walk if and only if it is balanced and strongly connected. So let's see if this graph is balanced and strongly connected. So if we check for balanced, we want to check that the in degree is equal to the out degree for each vertex. Okay, so let's start by looking at this vertex. The in degree is 1, we have one edge coming in, and the out degree is also 1, we have one edge going out. Okay, so that's good. Now let's look at this vertex here. The in degree is 1 and 2, and the out degree is also 2. Now let's look at this vertex, bottom right. The in degree is 3, but the out degree is 1. So that means this graph isn't balanced. Okay, so there's no closed Eulerian walk by the theorem. Okay, so by the theorem above, there is no closed Eulerian walk since the graph is not balanced. So now I want you to draw a directed K5. Remember, this is the complete graph on K vertices, or on 5 vertices, sorry. So we have 5 vertices and they're all adjacent to each other. And we want it to be directed. So you want to draw in arrows on all of those edges. But we want it to have a closed Eulerian walk. So think about that for a while and see if you can come up with one. Okay, so there are multiple ways of doing this, but I'll show you my answer. So remember, K5 looks like a pentagon with a star inside. Okay, and we want to draw arrows on these edges so that there's a closed Eulerian walk. So one way of doing it is this. Drawing these arrows here. Let's see. And then that one. Okay, so where's the closed Eulerian walk? I'll draw it in for you. You get a different color. So the closed Eulerian walk, we can follow these edges right here. Notice it's not a path because we visit each vertex more than once, but we do visit each edge only once. All right. Okay, so this is an example of a tournament. Tournament is just a complete graph that's directed, so it has arrows on the edges. So now let's talk about Hamiltonian paths and cycles. So a Hamiltonian path is a path that visits each vertex exactly once, okay? So the exactly once comes from the fact that it's a path, but it visits all of them, okay? That's where this each comes in. So just like an Eulerian walk visits all of the edges, a Hamiltonian path or walk visits all of the vertices. And similarly, a Hamiltonian cycle, okay, so it's a path that starts and ends at the same vertex, visits each vertex exactly once. Okay, and this doesn't have to be for a directed graph, but you can define this for a directed graph just by making sure you follow the edges in the correct direction. So in this example, does this graph have a Hamiltonian cycle? So pause the video and try to see if you can draw one or explain why there isn't one. Okay, so a Hamiltonian cycle, okay, we want a cycle that visits each vertex exactly once. All right, so the problem is kind of the fact that these two parts are detached, except that they're connected only at this vertex here in the middle. So let's say we started at this vertex, okay? We go through this triangle, okay? And then we either come back here, but we won't have visited these vertices, or we go along here, but then when we come back here, it won't be closed. We have to get back to the vertex we started at. Okay, so we can't start inside this triangle. For a similar reason, we can't start inside this part over here. And what if we start in the middle? If we start in the middle, well, we have to pick a side to go to first. Let's say we cover this triangle, and then we're back here, okay, and we haven't gotten to any of these vertices. All right, so no, there's no Hamiltonian cycle in this graph. So we have a few theorems that can help us decide if a graph has a Hamiltonian cycle. So theorem 1 says that if we have a graph with n vertices, it's the number of vertices we have, and n is greater than 2, then there's a Hamiltonian cycle if the degree of each vertex is at least n divided by 2. And we have another theorem, this is for directed graphs, right? So every tournament, remember that was a directed complete graph, has a directed Hamiltonian path. Okay, so it has a path that visits each vertex exactly once, following along the arrows. So let's use these to answer these questions. Suppose a connected graph G has 4 vertices. Call them V1, V2, V3, and V4. We'll also assume the degree of V1 is 3, the degree of V2 is 2, the degree of V3 is 2, and G does not have a Hamiltonian cycle. Then what's the degree of V4? So pause the video and try to answer this. Okay, welcome back. Let's reason through this. Okay, so what do we know about graphs that have Hamiltonian cycles? Okay, well, we know that if the degree of each vertex is at least n over 2, then we have a Hamiltonian cycle. But we're told that this graph does not have a Hamiltonian cycle. So it's not possible for the degree of each vertex to be at least n over 2. So n here is 4. We have 4 vertices. Okay, and if the degree of each vertex is n over 2, which is at least n over 2, then G has a Hamiltonian cycle by theorem 1. Okay, but it doesn't have a Hamiltonian cycle, so we want to make sure that it's not true that all of the vertices sorry about that. Okay, so we want to make sure it's not true that all of the vertices have degree at least 2. Okay, so the degree of V4 has to be either 0 or 1, but G is connected. So can the degree of V4 be 0? No. Otherwise, we'd have a vertex all by itself and the graph would not be connected anymore. So the degree of V4 has to be 1. Oops. Has to be 1 by theorem 1 and the fact that G is connected. Okay, so now another example. I want you to pause the video and draw a tournament on 4 vertices and then find a Hamiltonian path in it. We know there has to be one by theorem 2. Okay, welcome back. So let's draw one. First we draw K4, because it has to be the complete graph. Okay, and it has to be directed, so we can just draw random directions on here. Okay, and there has to be a Hamiltonian path. So let's find one. Let's get a different color. All right, what if we start here? The only way to leave this vertex is this direction. Go down here. Okay, now what can we do? Let's see. Want it to be a Hamiltonian path. So we want to get to all of the vertices at each vertex exactly once. Right, so the last thing to do would be to somehow connect this vertex. Right, we could do it by following that edge. Okay, so there's our Hamiltonian path. Oops. Okay, so now suppose we're given a set of results of a round-robin tournament. So that's a tournament where each team plays every other team. So first, how can we model this as a graph? So each team has already played each other, and we know who has won. Assume there are no draws. Is it always possible to rank the teams in order from winner to loser? So pause the video and think about that for a minute. Okay, welcome back. So first, how can we model this as a graph? Well, we can let our teams are the vertices, because those are our objects. Okay, and we draw an edge between them if they played against each other. Well, they all played against each other, so what kind of graph is it? It'll be complete, right? There will be an edge between each pair of vertices. So the graph is complete. But the information we don't have in this graph so far is who beat whom. Okay, so we can actually use a directed graph here, and we can draw the edges so that they are pointing towards the team that won the game, that won each game, the game that represents that edge. Okay, so this is what we called a tournament. Does it make sense now why we call it a tournament? Okay, so we've modeled this as a graph. We want to know, is it always possible to rank the teams in order from winner to loser? So let's go back to theorem 2. Every tournament has a directed Hamiltonian path. Okay, so we'll have a path in there that includes all of the vertices. So this directed Hamiltonian path would, in theory, rank all of the teams. So this is a tournament, so it has a directed Hamiltonian path by theorem 2. Okay, but can we rank them from winner to loser? Do we always necessarily have a first place and a last place? Well, what if that Hamiltonian path is a Hamiltonian cycle? Okay, then we have this loop that goes around and there's not a designated starting and beginning. So if the Hamiltonian path is a cycle, we don't have a winner or a loser. Okay, so the answer is no. However, if the path is not a cycle, we can rank the teams in order from winner to loser. Okay, and our last problem, an interesting application. We want to write the integers 1 through 15 in a line so that each two adjacent integers add up to a perfect square. So a perfect square is like 1, which is 1 squared, 4, which is 2 squared, 9, which is 3 squared, etc. So think about how this relates to graph theory and try to solve this on your own. Pause the video and then come back. Okay, so welcome back. Let's think about how we can solve this using a graph. So I'm going to first write out the numbers 1 through 15. And below, I'm going to write the numbers in 1 through 15 that when we add it to that number in the column I'm picking, we get a perfect square. Okay, so what can we add to 1 and get a perfect square? Let's see, we can add 3 to it to get 2 squared. We can add 8 to it to get 3 squared. And we can add 15 to it to get 4 squared. Then for 2, we can add 2, we can add 7, and we can add 14. For 3, we can add 1, 6, 13. For 4, we can add 0, we can add 5, 12. Notice these will all be descending in each row here. Okay, so I will skip ahead to having filled out this whole thing. Why don't you do that on your own? You can pause the video so that you don't get too far ahead of you. Okay, I'm back. So now we have our row filled out. Notice we got this new row in here. Okay, for the ones that add up to 25, which is 5 squared. Okay, now we want to try to draw this as a graph. So what should our objects be and what should our connections be? So our objects can be the numbers 1 through 15, and we can draw a line between them if they add up to a perfect square. Okay, so I'm going to draw that graph and skip ahead in my video, so I'll see you then. Okay, welcome back. You can pause the video and check that your graph is the same as mine. So what do we want now that we have this graph? We wanted to write the integers 1 through 15 in a line so that each two adjacent adds up to a perfect square. Okay, so what we're looking for is a Hamiltonian path. Right, so we can try to draw one here. Change my color one last time. Okay, and where should we start? Well, if we want to visit each vertex, then notice that at 8 and 9, okay, these two vertices have degree 1. So we're going to have to start at one of them and end at the other. Notice this means that there's no Hamiltonian cycle. Okay, if we leave 8, there's no way of getting back to it. Same for 9. All right, so let's start with 8 and follow along to 1. And then where should we go? We have to be kind of careful about this. So let's say we go to 3, then 6, then 10, then 15. Okay, that's not going to work. So let's try again. Go from 1 to 15, to 10, to 6, to 3. Don't want to go back to 1. Okay, so now to go to 13, 12, 4, 5, 11, 14, 2, 7, and then back to 9. So we found our Hamiltonian path, and by following along the vertices that occur in this edge, you can write down the integers 1 through 15 so that each 2 adjacent adds up to a perfect square. So I thought that was a fun application to end this lecture with, and I'll see you in the next one for our last lecture on an introduction to graph theory.